Welcome to our second learning workshop. We are going to be covering ionic and covalent naming and writing of formulas, and also what ionic bonding is versus covalent bonding. So, first of all, we want to ask ourselves, what are ions? So, an ion refers to any particle that is either a positive or a negative charge. Don't you love the little cartoon? Pretty great, I thought. Ions can actually be single atom ions, in other words, just a single atom of an element that's lost or gained electrons, or an entire molecule that has gained or lost electrons. And that entire molecule that's gained or lost electrons is called a polyatomic ion. Right? Just a little basic background. So this little image is kind of a representation of how ions are formed. Now, let me ask you real quick, have you gone over any of this in class as far as like ionic and covalent naming and writing?
For me, just a little bit.
Okay. Okay, so for most of you, this is pretty new. Okay. You might have seen it probably in high school, or if you remember back that far. I know that some have not had the greatest experiences in as far as like chemistry in high school. Um, Hard to find good teachers these days. But yeah, basically, when atoms get close enough to bond with each other, some have a greater attraction for electrons than others. So that attraction is referred to as electronegativity. So in many cases, um, there's not that big of a difference in electronegativity, and they just share the electrons as a result. They both share the electrons together. But if two atoms have very big differences in electronegativity, one atom will be completely stripped of its electron by the other atom. So one completely gives away its electron and the other one completely takes it. The atom that loses an electron becomes positive and is called a cation because electrons are negatively charged, right? So if you lose your negative attitude, you become a positive person, right? So, yeah, losing a negative, you become positive. An atom that gains an electron is negative, and that would be called an anion. So it's a really cool video that I want to show you, but it doesn't love me right now. So I'm going to have to show it to you via some other method. I'm actually going to do this instead. Share my entire screen. They can't stop me. All right. Bam. All right. Here we go.
Most atoms don't ride solo. Instead, they bond with other atoms.
That's it. No, I'm just kidding. I want to mute myself so I'm not like...
Now, bonds can form between atoms of the same element, or atoms of different elements. You've probably imagined bonding as a tug of war. If one atom is really strong, it can pull one or more electrons off another atom. Then you end up with one negatively charged ion and one positively charged ion. And the attraction between these opposite charges is called an ionic bond. This is the kind of sharing where you just give away your toy to someone else and then never get it back. Table salt, sodium chloride, is held together by ionic bonds. Every atom of sodium gives up one electron to every atom of chlorine. Ions are formed, and those ions arrange themselves in a 3D grid called a lattice, in which every sodium ion is bonded to 6 chloride ions, and every chloride ion is bonded to 6 sodium ions. The chlorine atoms never give the sodium atoms their electrons back. Now, these transactions aren't always so cut and dried. If one atom doesn't completely overwhelm the other, they can actually share each other's electrons. This is like a potluck, where you and a friend each bring a dish, and then both of you share both dishes. Each atom is attracted to the shared electrons in between them, and this attraction is called a covalent bond. The proteins and DNA in our bodies, for example, are held together largely by these covalent bonds. Some atoms can covalently bond with just one other atom, others with many more. The number of other atoms one atom can bond with depends on how its electrons are arranged. So, how are electrons arranged? Every atom of a pure, unbonded element is electrically neutral because it contains the same number of protons in the nucleus as it does electrons around the nucleus. And not all of those electrons are available for bonding. Only the outermost electrons, the ones in orbitals furthest from the nucleus, the ones with the most energy, only those participate in bonding. By the way, this applies to ionic bonding too. Remember sodium chloride? Well, the electron that sodium loses is the one furthest from its nucleus. And the orbital that electron occupies when it goes over to chlorine is also the one furthest from its nucleus. But back to covalent bonding. Carbon has 4 electrons that are free to bond. Nitrogen has 3, oxygen 2. So carbon is likely to form 4 bonds, nitrogen 3 and oxygen 2. Hydrogen only has 1 electron, so it can only form 1 bond. In some special cases, atoms can form more bonds than you'd expect, but they'd better have a really good reason to do so, or things tend to fly apart. Groups of atoms that share electrons covalently with each other are called molecules. They can be small. For example, every molecule of oxygen gas is made up of just 2 oxygen atoms bonded to each other. Or they can be really, really big. Human chromosome 13 is just 2 molecules, but each one has over 37 billion atoms. And this neighborhood, this city of atoms, is held together by the humble chemical bond.
Yeah, so, oh, I didn't realize that my mic was off. Ha, okay. So, um, I was talking like during that time, and I don't think I didn't realize that, or I don't think I realized it wasn't. But yeah, no, you're absolutely right. Valence electrons have more energy because of the potential energy. It's not actually because of the kinetic energy, because as you might expect, for the electrons that are closer to the nucleus to not end up crashing into the nucleus, because there's a stronger force of attraction between the nucleus and the electrons that are closer to them, then one might expect that those electrons closer to the nucleus might have to actually move faster, might have to have a greater velocity. But the truth is that when it comes to why the valence electrons are considered to have greater energy, it's because of their potential energy. They're further from the nucleus, and therefore they have a greater potential energy than electrons closer to the nucleus. So you're absolutely correct. I hope that adequately answers it. And thank you, Dr. Neely, uh, um, for your explanation as well.
And thank you, Professor Depa, and Ethan. Excellent question. Thank you, Ethan.
So let's comparing bonding types, ionic to molecular. The first question we want to ask ourselves is, what happens to electrons? So what happens to electrons based on that video? What happens to electrons in ionic compounds? And feel free to turn on your mics, or you can also just talk via the chat if you prefer.
So in ionic compounds, there are two elements or molecules that have one has let go of an electron and is thus a different charge than the ion that picked up the electron, so it's just naturally attracted to that space, and so they just kind of float around with each other, I guess.
Yeah. So the electrons, one completely is taken away, and the other completely gains it. Yep. And they're oppositely charged. Uh, they're now oppositely charged, and so they kind of stick together like magnets. Very good. What happens to electrons in molecular compounds?
An electron is just completely shared between the two.
Yeah, a pair of electrons or more than one pair of electrons is shared between the two atoms. Exactly. So that's the biggest difference between ionic and molecular. One completely gives the electrons, the other shares them. And so how does this affect the atoms? The atom that loses an electron becomes positively charged, as you mentioned, so it's a cation. The one that gains the electrons becomes negatively charged. Now, and for the molecular compounds, two nuclei of the atoms pull each other in a tug of war, and that kind of causes them to basically get kind of stuck together because neither one is willing to let those shared electrons go. So why do atoms gain or lose electrons? Any ideas? And this is a kind of a tricky question. I'm curious to see if you all have any answers to it. Why do atoms gain or lose electrons in ionic bonding?
So the element that is closer to filling a valence electron shell is going to pull harder on something that isn't. Like, so hydrogen only having one in its shell is going to be pulled really hard against something, I think, like francium that needs like one or two, I think, or something like that.
Well, for a francium only has one valence electron, but yes, you have the right idea. And Elaine mentioned to fill 8, so that, like the idea of the octet rule. You're absolutely right. Yeah, you have the right idea. Basically, what it is that they're trying to get to the most stable configuration they can possibly be. And the most stable configuration that they can possibly be is a noble gas configuration. This is with a completely filled outer shell. Now, interestingly enough, you mentioned hydrogen, but hydrogen isn't actually terribly apt to, if it loses its electron, it actually has no valence electrons. If it gains an electron to be like helium, then it has a negative charge. When hydrogen reacts with, when hydrogen is part of an ionic compound, like with a metal, like a sodium or something like that, it actually does gain an electron from sodium or from francium or from one of those more active metals. But that happens fairly rarely because hydrogen does not have a tremendous amount of pull, shall we say. But yes, your idea basically that they're trying to get a total of 8 electrons is absolutely right. They're trying to get a noble gas configuration to be like the closest noble gas. And that's for the same reason atoms share electrons. The interesting thing with the sharing of electrons is it's kind of like, for example, let's say, growing up, I have 6 brothers and sisters. Okay, so so growing up, we would pool our resources together all the time because we were actually fairly poor, but my brothers and I we would pool our money together and maybe like get a particular game that we wanted, and if we did, we would consider it a shared game. So we would all have access to it, and we considered it all of ours. So when atoms share electrons, each atom considers the electrons all of theirs. So if with the shared electrons they have 8 electrons around them, they're pretty happy. And that's one way to kind of think of it. But once again, they're trying to get a noble gas configuration. They're trying to be like the noble gas by having 8 electrons in their outer shell. And the bonding, what does the bonding look like? Well, that comes down to what you saw in the video. The 3D pattern called a lattice of alternatively charged ions. That's kind of what an ionic compound looks like. Covalent. Each group of bonded atoms is a separate molecule, kind of like you saw in the video. Yes.
So I just briefly wanted to add that in general, we can say that metals tend to lose electrons and become positively charged, whereas nonmetals tend to gain electrons and become negatively charged. And these atoms tend to lose or gain electrons to feel like the noble gas nearest to them.
Mm-hmm. Yeah, you're not wrong. That's absolutely right. Um, the nonmetals are on the right side of the periodic table, so they're more likely to gain electrons, and metals are on the left side of the table, more likely to lose. That's absolutely right. Now I want to show a quick little video, and my little thing is not working properly. So I'm going to share it from here. Let's go ahead and do it. Here we go. Bam.
When a piece of sodium metal is added to a flask of chlorine gas, a vigorous reaction takes place that releases a lot of energy, and sodium chloride, a common table salt, forms. The chemical details of sodium chloride formation are similar to the formation of many other simple ionic compounds. Let's view the process of ionic compound formation on the atomic scale. Many chemical reactions occur through a series of steps. In the process of ionic compound formation, the key step is electron transfer from the metal to nonmetal to form oppositely charged ions. As a chlorine molecule approaches the sodium surface, yet before it makes contact, electron transfer occurs. Then a series of rapid steps, too complex to detail here, forms free chloride ions that are attracted to sodium ions and energy is released. Let's isolate the key step and examine a simplified version of it. Electron transfer from a metal atom to a non-metal atom. The sodium atom has 11 protons and 12 neutrons in its nucleus, and 11 electrons around the nucleus. The chlorine atom has 17 protons and 18 neutrons in its nucleus, and 17 electrons surround it. The sodium atom transfers an electron to the chlorine atom, and the ions attract each other and release energy. The loss of the electron converts the sodium atom into a smaller, positively charged sodium ion, Na+, while the gain of the electron converts the chlorine atom into a larger, negatively charged chloride ion, Cl-. Let's view this essential step once more. Electron transfer and ion attraction occurs countless other times between the sodium and chlorine. The large quantities of energy released vaporize tiny clusters of ions, and these attract others and release more energy. The clusters eventually aggregate and coat the walls of the flask. And even though table salt is not obtained this way, the product of this reaction consists of the same regular array of ions that makes up any sample of crystalline sodium chloride.
Shame on me. I thought that was awfully cool, so I had to share it with you. Forgive me if that was unnecessary, but I thought it was kind of fun. All right, so let's go back and take a look. So here's our sodium chloride. This kind of a structural representation of this face-centered cubic lattice. Each ion has 6 neighbors to it. Now, the important thing here is that we can't really describe ionic compounds as forming molecules. Instead, we have this special name for it called a formula unit. And a formula unit is the smallest whole number ratio, or basically the empirical formula for an ionic compound. So when we're doing conversions later on in chemistry, which is going to come up very soon, we're going to actually have to refer to formula units instead of molecules when it comes to ionic substances. Here's a nice big picture of sodium chloride. I kind of like it. Now, let's talk about writing formulas for ionic compounds. So this little ion chart here, it can be useful for like finding the charge of different ions. You'll notice that, for example, here we go. So for example, see if you've got fluorine here. Fluorine is only it has 9 electrons and 9 protons as a neutral atom. It wants to be like the closest noble gas, which is neon, which has 10. So if you get from 9 to 10, it has to gain 1 electron. Since fluorine will gain 1 electron, it becomes a -1 charge. Fluorine likewise has 17, and it wants to be like the closest noble gas, argon, which has 18. So it will likewise gain 1 electron, and therefore have a -1 charge. This pattern kind of repeats itself, so that all of the atoms in this column, fluorine, chlorine, bromine, and iodine, they all are going to tend to have -1 charges, and they're all going to tend to gain 1 electron. Likewise, oxygen, sulfur, and selenium are all 2 away from the closest noble gas, and so they'll tend to gain 2 electrons. Now your professor is probably not going to give you a chart like this that shows you the charges of the different ions. He's going to actually expect you to be able to figure it out just by looking at the periodic table. But if you understand that principle, that they're trying to be like the noble gases, it's actually not as hard as you might think. So oxygen is 2 electrons away from neon, so it'll gain 2, it'll be -2 charge. Sulfur goes from 16 to 18 and has to gain 2 electrons, -2 charge, etc. And similarly with nitrogen and phosphorus, they're going to gain 3. Remember that metals, this area down here, metals don't gain electrons. So they are going to tend to be positively charged, if charged at all. On the other side, you'll see a similar scenario. Hydrogen's kind of the weird one. It does tend to lose electrons. It does tend to lose its only electron, but it's not trying to be a noble gas in that way. However, lithium has 3 electrons. It's going to want to lose 1 to be like neon. Sodium has 11 electrons. It wants to lose 1 to be like neon. Lithium wants to lose 1 to be like helium. Now sodium wants to lose 1 to be like neon. And the potassium, which has 19, is going to want to lose 1 to be like argon. So they're all trying to lose or gain electrons to be like the closest noble gas. And so this nice, neat little pattern, +1, +2, and then as you go from the other side, -1, -2, -3. The only other thing that I wanted to mention to you is this very unique pattern in the middle of this sea of blue. Now, this sea of blue is referred to as the, I guess you could call it the transition area. But basically, these are areas that are filled with a combination of transition metals and atoms that tend to just not get any charge whatsoever. All right. But this little triangle here, this little staircase, starting with silver and going up to aluminum, I like to sometimes refer to it as the magic staircase because for some reason, and you'll understand, and I'll be able to explain the reason in more depth later on, but for now, you don't have to worry about the reasoning here. Aluminum is always going to want to lose 3 electrons. In aluminum's case, it makes sense because if it loses 3, it'll be like neon. It's not as easy to see with gallium or indium, but the same reasoning does apply. So this column, the aluminum, gallium, and indium are all +3s. Zinc and cadmium are always +2 charges, and silver is always a +1 charge. Unlike the other transition metals in this blue area here, which can have multiple charges, this triangle here, this staircase, is always stuck with the same charge. The 3+3s, 2+2s, or 1+1. It's a nice, neat little triangle for that purpose. Easy to memorize. So when writing formulas for ionic compounds, the first thing we want to do is identify the ions present along with their charges. The periodic table can't help you with polyatomic ions. Unfortunately, you just need to memorize those. There's 8 primarily that you need to memorize, unless your professor gives you a polyatomic ion chart. Now, has your professor mentioned anything about allowing you to use a polyatomic ion chart?
Yes,
Okay.
yes. Normally, we just ask the students. There's like maybe 7 or 8 of them. There's not too many of them, and we just ask them to memorize them. And once they practice it, then it's not so difficult.
Yeah. Most professors do require you to memorize them. I'll emphasize and point out the most important ones in a little bit. Okay, so first identify the ions. So like for example, with the compound magnesium phosphate, have to recognize, well, magnesium is going to be Mg, and that's a metal that's on the periodic table. That's going to be a +2 charge. So I'd write a 2 plus. And phosphate's a polyatomic ion, so that's one of those you have to memorize. And that it just ends up being a PO4 3 plus charge. Next, find the lowest common multiple, or LCM, of the two different charges. So what does that look like? So for magnesium phosphate, the charge of magnesium is a +2, so multiples of 2 would be like 2, 4, 6, 8, 10, etc. For phosphate, multiples of 3, because it has a charge of -3, would be 3, 6, 9, etc. So the lowest common multiple, the lowest multiple that both of the charges have, is this 6. Once you know that, you can determine how many of each ion is needed to get the total positive charge to equal the total negative charge. Because that's the basic principle. With any ionic compound, the total positive charge must equal the total negative charge. So in this case, how many magnesiums do you need to get a total of 6? 2 times 3 is 6, so I need 3 magnesiums to get a total of positive 6 charge. How many phosphates do I need to get a total of 6? I need 2 times -3, or 2 phosphates, to get a -6. And note, if I'm looking at the number of the multiples, it's the second multiple of phosphate, so I need 2 phosphates. It's the third multiple of magnesium, that's 2, sorry. It's the third multiple of magnesium, so I need 3 magnesium. Alright, so then once you know how many of each ion you need, then you can go ahead and write the formula. So we already figured out that we needed 3 magnesiums and 2 phosphates, so I just write Mg with the subscript 3. The subscript tells me how many. This tells me how many magnesium. And then so that tells me how many magnesiums. And the phosphate, I need 2 of them. So I have 2 phosphates. That tells me I have 2 PO4s. So let's take a shot at writing the chemical formulas for each of the following compounds. I'll go through the first one together with you, but then let's have you try the other 2 on your own. So calcium bromide. So what's the symbol for calcium? What's the ion symbol for calcium? So that is symbol and charge. Calcium Ca, very good. And what's the charge? +2, very good. So I'll write Ca, I don't know what that was. Ca is the 2 plus charge. Okay, cool. Now what's the charge of a bromine ion? What's the bromine ion going to look like? It's a minus charge, and bromine, the symbol is what? Br, very good. So I got a Br with a -1 charge. So the lowest common multiple of 2 and 1 is what? 2, exactly. So 2, 4, 6, 1, 2, 3, 4. So 2 is the lowest common multiple, and therefore I'm going to need one calcium to get a total of 2 plus. And how many bromines do I need to get a total of 2 minus? 2. There you go. So I write Br2. And this is my formula for calcium bromide. Does that make sense? Now I will say this. There is another method that's oftentimes taught in your chemistry classes, and it's a method I'm not terribly fond of. It's sometimes referred to as the crisscross method. So they take the charge here and they put it in front of the calcium, and then you take the charge for calcium, put it in front of the bromine, but they only do the absolute value of it, and then you get, like, CaBr2. The problem that I have with this is the following. First of all, it confuses the ionic charge, the superscript, with the number of atoms, the subscript. Subscript and superscript do not tell you the same thing. This 2 down here does not tell you the charge of bromine. It actually doesn't even tell you the charge of calcium. It happens to coincide with the charge of calcium, but it doesn't tell you the charge of calcium. What it's telling you is that you have 2 bromine ions. And so I actually did a research study for my master's degree that compared these two, that compared this method of doing ionic formulas with the other method of doing ionic formulas. And um, what I discovered is that there is some evidence that students who use the crisscross method end up, or students who are taught with this crisscross method, end up with a less accurate vision, a less accurate understanding of ionic bonding in general. And in my own personal experience, they seem to make more mistakes when writing down chemical formulas. That said, you are free to use the crisscross method if you prefer. All right, so let's go ahead and do B and C. When you have an answer, go ahead and feel free to hit the hit the raise hand sign. It's on the bottom middle of your screen, like that. Yep, exactly. Ethan, you already have answers for him?
Just B. I'm sorry. Do you want C as well?
Yes, yes. Let's do B
Okay.
and C,
Gotcha.
and we'll give you a minute, a short minute. Go ahead and do that, and then we'll go over it together. We'll see what you get.
I have B. I'm working on C. I don't know if I'm right or not. B, I know I'm right. C, I'm not sure.
No problem. Well, let's take a look at them. All right, so you got aluminum oxide. What did you get for that? Absolutely. There you go. It should have been Al2O3. Excellent job. All right, what about zinc nitrate? What do we get for that one? Perfect. Perfect. Michael, you are right on track. ZnNO3 2.
So I made a mistake at some point when doing mine. I got zinc 3 NO3 too somehow.
Yeah, no, and so here's the thing. So what is the charge of zinc?
It's 2 plus.
Yeah, so zinc is a 2 plus charge. And what is the charge of nitrate's NO3, right? What's the
Yes.
charge of NO3?
I don't know. I guess I thought it was 3, but that's
It's
not. That's the
actually a
oxygen.
-1.
Shoot.
This is
Okay.
actually a -1 charge. So that's a good point. So let's go take a second to go over. I want to take a second to go over the most common polyatomic ions, the ones that you're going to really need to have memorized, because they show up honestly 95% of the time or more. And yes, I'm just making up that number, but from my experience, it's in the high 90s that whenever you get a question on a quiz or a test or anything like that, the polyatomic ion that you're given ends up being one of these 8 polyatomic ions. So there's, actually, let me go ahead, we're going to change this to black. Okay, so NH4, and this is a positively charged polyatomic ion. Um, and then you have, let's see, NO3, ClO3, OH minus, um, C2H3O2 minus, and this is sometimes also written as CH3 COO And then you have SO4, 2 minus, and then you have CO3, 2 minus, and then last but not least, you have PO4, and that's a 3 minus. And so the names of these are ammonium, nitrate, oh, whoops, I forgot the R. Try that again. Okay, try that again. All right. Nitrate, R-A-T-E. And then you have chlorate, C-H-L-O-R-A-T-E. And then you have hydroxide. This one's a little bit very common, but it's also, the naming pattern doesn't seem to fit in with everything else. I don't know why it did that weird thing with the random large line. Fix that. Anyway, hydroxide. And then on the other side, you have acetate, the C2H3O2. That's a -1. And then the sulfate, -2. So most of these are -1. You have 1 plus 1. You have 2 minus 2s, sulfate and carbonate. And then you have phosphate, PO4 3 minus phosphate. Now I wish I could tell you that there was some clear pattern when it came to charge or naming or whatever, but unfortunately there's really not. These are just, unfortunately, you kind of end up just having to memorize them because, for example, phosphate and nitrate, both of them are oxyanions, and both of them, nitrogen and phosphorus, are in the same column, but one of them's a -1 and the other's a -3. Um, Chlorate is ClO3, but it has a -1 charge just like nitrate, not in the same row and not in the same column. CO3 has a -2 charge, but it is way out there, you know? There's really no clear rhyme or reason to it. It's kind of all over the place. Now, there is actual good reason for why these charges are the way they are, but the explanation is complicated and it's not worth going into at this point in time because you simply don't have the background knowledge that you need at this point. It would just be unnecessarily burdening you with stuff that you're not ready for. At this point in time, it's just best to memorize these polyatomic ions. Now, I will also mention you may be responsible for certain derivatives. For example, when you have these oxyanions, that have 3 or 4 oxygens, if they have one less oxygen than their standard ATE ion, they get a different ending. They get an IPE ending. So like for example, NO2 minus would be a nitrite instead of a nitrate. Yes.
Something that might, a trick that might simplify this is to associate the -1 anions as nitrate, NO3 minus, and nitrite, NO2 minus, and then the -2 anions as sulfate, SO4 2 minus, and sulfite, SO3 2 minus. Maybe that helps a little bit.
Yeah, I mean, the important thing to mention is that the ITE ending here, it and the dropping of one oxygen does nothing to change the charge. The charge is still the same. It still works the same in every single way. The only difference is that when you drop an oxygen, the name changes from ITE to AT or ATE to ITE. So if you had ClO2, what would that be called? Um, Sorry, I wasn't quick enough on the draw. Oh,
Chloride.
chlorite. Yeah, exactly. Very good. Okay, so that's basic. That's basically it for that. Okay. And just as a extra thing, so you only have one -3 polyatomic ion. You have two -2 polyatomic ions, and the rest are all -1s except for ammonium, which is a +1 polyatomic ion. Okay. So yes, the transition metals. No, the transition metals are called transition metals because they can have multiple different charges. Remember, zinc is actually, it's in the transition metal area, but it's not a transition metal in the sense that it doesn't have multiple charges. It's only one charge that it's capable of having. The magic staircase group of elements: silver, zinc, cadmium, aluminum, gallium, and indium. They only have one charge that they can have, silver +1, um, zinc and cadmium +2, and aluminum, gallium, and indium +3. However, if you take any other of those polyatomic ions, things like manganese or iron, iron can have a +2 charge, can have a +3 charge. Copper can have a +1 charge, a +2 charge. Um, Manganese can have a +2 charge, a +3 charge, a +4 charge, a +5 oxidation number, a +7 oxidation number. So I mean, these can have a lot of different charges. So when you're given a transition metal, you have to figure out the charge based on what it's bonded to, and that's actually what we're going to hit next. So it says, name the cation first. So guidelines for naming ionic compounds. First, we have to figure out the name of the cation, and we figure out the name of the cation by usually if it's a metal, the name of the cation is the same as the name of the element. So aluminum is simply called Al3+ is just called aluminum. If the metal can have multiple charges, like you mentioned, it's a transition metal with multiple charges, you have to indicate its charge with a Roman numeral. So, for example, lead with a 4+ charge would be called lead with parentheses 4. Copper with a +1 charge would be called copper with a Roman numeral 1. From there, then you name the anion. And for a nonmetal monatomic ion, a one-atom ion, you just change the ending to IDE. So you use the first syllable and then change the ending to IDE. So oxygen becomes oxide, chlorine becomes chloride, phosphorus becomes phosphide. The ending changes to IDE. For polyatomic ions, there's no change in the name of the ion. You just write the name of the ion exactly the way it is. So CO4 3 minus, you know it's called phosphate, you just write phosphate. You don't have to worry about any ending changes. That's kind of a brief overview of naming. So let's go ahead and take a look. So how would we name this first one? And by the way, feel free to turn on your microphone. I certainly don't mind if you turn on your microphones. It's actually kind of a little bit more fun if we can all like talk to each other and hear each other. However, if you don't want to turn on your microphone because of noise or whatever, and you want to just answer in the chat, that's fine too. But what is the name for this first one?
How about aluminum sulfate?
Aluminum sulfate, absolutely. Aluminum sulfate. No Roman
Yes.
numeral necessary. Very good. What about the next one?
Ammonium sulfide.
Ammonium sulfide.
Excellent.
Absolutely, ammonium sulfide. Very good. All right, and ZNO?
Zinc.
Yeah, zinc oxide. Very good. And does anybody know what zinc oxide is used for? This is extra bonus question.
Is that the stuff you put on your nose when you go out of the sun?
Yes.
Yeah, sunblock. Absolutely. That's zinc
Sunscreen. You
oxide.
nailed it.
All right, what
Was
about
I
AgOH?
correct?
What do you got there?
Was I correct, or I was just joking?
No, you're actually correct. Zinc oxide, that's the stuff they put on your nose like to block out the sun.
And
Kind of a
it
mineral
is
sunblock.
right. If you don't rub it in, it's actually very white. So people that are very sensitive about using their sunscreen, they actually are conspicuous because they intentionally don't rub it in, and it definitely looks like they have sunscreen on.
Yeah, that's true. All right, so what's AgOH?
Silver hydroxide.
Silver hydroxide. Excellent.
Yes.
All right. Well done. You guys nailed this.
Oh,
You're picking up
before we move on, just really quickly, has anybody used the Blackboard Collaborate mobile here? Is anybody using their mobile device to get in here? Okay, no problem. Thanks.
Okay. Well, let's go over writing names for ionic compounds with transition metals because this adds a little extra complication to it. So if you're writing the name for a compound with a transition metal, you have to calculate the total negative charge from all the anions first, because negatively charged ions or anions are always pretty consistent about the charge that they have. They have a particular charge, and you can figure it out either from the memorized polyatomic ions or from the periodic table. Their charges don't change. But since the positive charges do change, we sometimes have to figure out what the positive charge is based on the negative charge. So we calculate the total negative charge, and remember the principle of ionic compounds is total negative equals total positive. You then simply divide the total positive charge by the number of positive ions. Divide the total charge by the number of ions to get the charge per transition metal. So, for example, we have iron sulfate here, the Fe2SO43. Well, I know that this SO4 has a -2 charge. And if it says SO43, there's 3 of the SO4 ions. So -2, -2, -2 gives me a total of -6. I also know that there is 2 iron ions. So if it's a -6 total charge on that side, it's going to be a +6 total charge for the iron. I then simply divide the +6 by the fact that there's 2 iron ions, and that gives me a +3 charge per ion. Does that make sense? Cool. So the name of the compound then would be called iron Roman numeral 3 sulfate, because the Roman numeral tells you the charge of the transition metal. Not how many there are, it tells you the charge of the transition metal. Okay, so let's practice on these. Let's take a stab at these. I'll give you a minute to go ahead and come up with your names for these compounds, and when you think you have them, just go ahead and raise your hand. Or type ready in the chat. Either is fine. Yeah, very good. The first answer. And don't feel bad if you're slow at these. Everybody is slow at these to start. But yes, okay. Elaine said chromium 3 sulfate. You're absolutely correct. Very good. Michael said iron 3 carbonate. That's not quite right. You were doing reverse crisscross, weren't you?
Yep.
That's the danger with reverse crisscross. Reverse crisscross will kill you, man. Yeah, you got to watch out for that. But yes, especially with polyatomic ions. 'Cause here's the thing. The key thing is to remember that the total positive charge has to equal the total negative charge. Carbonate's a polyatomic ion, right? What's the charge of carbonate?
-2.
-2. And so how many carbonates do you see here?
3.
Actually, it's just one.
Oh,
Remember,
1. I'm sorry.
carbonate is CO3.
That's right.
So this is just one carbonate, which means the total charge for the negatives is -2. And that means that the iron has to be what charge?
2.
Yeah.
I guess just a quick chiming in. I wouldn't distinguish the carbon on its own. I would just look at it as 2 units, the iron unit and the carbonate unit.
Yeah. Yeah. Whenever you have a compound that has a metal in front, that is invariably going to be an ionic compound as far as you're concerned. I mean, I know there are exceptions to that, but at the same time, they're not exceptions that you're going to really deal with. So as far as you're concerned, you see a metal in front, that is a ionic compound. An ionic compound, if you have more than 2 elements, that means you have a polyatomic ion. So for example, I see the CdOH2, I know that's polyatomic ion. I see iron, carbon, and oxygen, FeCO3, I know I have a polyatomic ion. Anytime there's more than 2 elements, it's polyatomic ion. All right, what about the next one? What's the next one?
Cadmium hydroxide.
Cadmium hydroxide. No Roman numeral?
No Roman numeral.
Well done.
Hydroxide has a -1.
Yeah, and the reason there's no Roman numeral is because why?
The hydroxide has a -1.
Nope, it's not because of that.
Well, then never mind.
You are correct. It is cadmium hydroxide, no Roman numeral. The reason is because cadmium is not a transition metal. Remember, it's one of those special magic staircase elements. Silver, zinc, cadmium, aluminum, gallium, indium. You don't need Roman numerals with those because their charge is always the same. +1 for silver, +2 for zinc and cadmium, +3 for aluminum and the other two, gallium and indium.
I think here it would really help if, and I'm trying to do it successfully so far, if we can launch that slide that really was able to show that stepwise fashion with those, with the silver. Oh yeah, there you go.
I'll draw my mock version of the periodic table. With that last element on the end. Actually, there's actually two. There's actually another one up there, but yeah. So yeah, aluminum, um, gallium, and indium. These are your +3s. There's 3 +3s. Then there's zinc, cadmium, 2 +2s. And then there's silver, 1 +1. That's the magic staircase. Above aluminum is boron, but we don't care about that. You'll care about it more in organic chemistry, but we don't care about it right now. Cool?
Thank you for that.
Yeah, no
I'm
problem.
sorry, you said silver is +1?
Silver is always a +1, yes. Copper, which is above it, can be a +1. See, copper is not part of the magic staircase. It can be a +1, but it can also be a +2, so it is not magic staircase element. You have 1 +1, 2 +2s, and 3 +3s. So just memorize that little magic staircase and you're good. All right, now what about the last one, MnO2? What do we get for that one?
I actually have the slides pulled up, so I actually know the answer for this. But I don't understand why. I know it's manganese oxide, but it's manganese 4 oxide, but I can't figure out why it's 4.
Okay, so what's the charge of an oxygen ion?
2 minus.
A 2 minus. So if we're looking at this, oxygen's a 2 minus charge. So O is a 2 minus. And how many oxygen ions do we have?
Okay, I see.
We got two O minus, two 2 minus oxygen. That's a total of -4, which means that that one manganese has to be a +4 to balance it out.
I guess. Well, yeah. I guess I was caught up in the other ions. That's just what they are,
Yeah,
and that one's actually 2 of that of the oxygen.
exactly. Yeah.
That makes.
And so, yeah, so that's a tricky one. This is also one of those where reverse crisscross will kill you. So you got to be careful with that. All right, cool. So let's name some covalent compounds. Since we nailed ionic compounds, we're doing pretty good. Let's hit the covalent compounds. Fortunately, these are a lot easier. It's all based on prefixes. So covalent compounds, it turns out that sharing can happen in a lot of different ways. So like for example, just between elements nitrogen and oxygen, you can have nitrogen monoxide, dinitrogen, monoxide, so N2O. You can have NO2. You can have N2O4. You can have N2O5. And all of these are actual, real compounds of nitrogen. So it has nothing to do with charges, because if it had charges, there'd only be one way to put them together. In this case, it's not based on the charge. It's just they can come together in different ways to form different shared structures, shared electron structures, different molecules, so to speak. So, yes.
Before we get into the naming of these covalent compounds, can somebody on the team re-explain to us the fundamental difference between molecular compounds and ionic compounds? Thanks.
That means you guys. So what is the key difference between... Oh, I am so sorry. My mic has been really, really quiet. I apologize. So that means she wants to know what's the difference between ionic compounds and molecular compounds in terms of their bonding structure.
So one is going to be a shared bond, and one of them is going to be more of a charge bond. Is that what you're looking for?
Yes.
Yeah,
yes.
absolutely.
Thank you, Ethan.
Exactly. The shared versus alternate charges, complete giving away and taking of electrons. So to name a covalent compound, all you need to do is name the first element with an appropriate prefix, as opposed to an inappropriate prefix, unless the prefix is mono. So there's no mono for the first element. So like for example, this first NO, I would not say mononitrogen monoxide. I would just say nitrogen. So this is I would just name the first element as an element, nitrogen. Now, if there are 2 of them, I would say dinitrogen. If there are 3 of them, I would say trinitrogen, etc. Then you name the second element with the appropriate prefix and change the ending to IDE. So in this case, the second element is oxygen. So once again, I'm going to take the first syllable and then drop it to IDE. So oxide instead of oxygen, oxide. But I need to put a prefix indicating how many there are, and there's only one, so it'd be nitrogen monoxide. And I can't remember, is that laughing gas? I think that's laughing gas. Nitrogen monoxide.
Yes, I don't remember if it was NO that's the laughing gas or N2O, but let me look it up. Hold on.
No problem. All right, so I've got some chemistry anthropology.
Okay, it is N2O, nitrous oxide.
Oh, okay. Ethan's asking a question. Is that because some weird chemistry anthropology, or is there a molecular significance to the reason why we don't use mono for the first element? Honestly, I think it's because chemists are lazy. I think we just don't like to write any more than we have to, and we're like, if there's only one in the first one, we can just write the name. Don't worry about it. Don't use it unless you have to. Yeah. So,
If chemists were really lazy, they wouldn't have such long names.
that's true.
Right then. Isn't that the truth?
Oh my goodness. Yes. Okay, so then so in the next one, this is going to be, of course, dinitrogen. Dinitrogen monoxide. Whoops.
Another common name for it is nitrous oxide or laughing gas, but you don't have to. You don't have to remember that. That's just if you're curious.
Yeah. And then like NO2, likewise, it's going to be nitrogen dioxide. And then N2O4, dinitrogen tetroxide. Now here's the interesting thing, and this is something I should mention here. When you have oxygen, for some reason, whenever you have, let me see, I'll underline these. Whenever you have any, like either mono or any of the prefixes ending in A, tetra, deca, nona, octa, hepta, and hexa, when you have oxygen in one of those prefixes, you end up dropping the last letter of the prefix. So like, for example, with regards to, let me change my color here. With regards to the last one, maybe you might think it'd be dinitrogen pentaoxide, but it turns out it's dinitrogen pentoxide. Pentoxide. Dinitrogen pentoxide.
My guess there is because we want to avoid the double vowels.
Exactly. Although it doesn't stop us from using the double vowel when it's triiodide. So
Good point. Good point.
Who knows? Who knows? But like, for example, Ni3. Ni3 is actually nitrogen triiodide. And that one you actually do use the double vowel. It seems to be only a thing that we like to do with oxygen. And my guess is they just did this to confuse students.
So once again, we have chemists to thank for this?
Yeah, pretty much. I can just see like the chemistry naming guys, the IUPAC guys, kind of like chuckling under their seats, like laughing at their students trying to figure out all these idiosyncrasies they built in. Look. Anyway, yeah. So there you go. All right, now let's do a little bit of naming. So what would be the name of this first compound?
Carbon dioxide.
You got it, carbon dioxide. So that's an easy one. What about the next one?
Dinitrogen
Also, I can agree.
pentoxide.
Dinitrogen pentoxide. What about P4O10?
Tetraphosphorus dioxide.
Tetraphosphorus what?
Dioxide. Or
Dioxide?
dioxide. Sorry.
Decoxide.
Dexoxide.
Yeah. You had the right idea, I think.
I just wasn't. I had it written down right. I just couldn't pronounce it.
No, I understand. And then N2O, what's that?
Laughing gas.
Yes, it is. What's the IUPAC name?
Dinitrogen oxide.
Close.
Dinitrogen monoxide. There we go.
Dinitrogen monoxide, exactly.
That's so
You only
dumb. I
don't
don't
need
know
a
why.
mono prefix with the first element.
Jeez.
No, what'd you say? I'm sorry.
It's kind of dumb that we put monoxide on the second one, but not the first one. I don't I don't
Yeah.
get that.
Yeah, I'm not entirely sure why either. Yeah. It would be nice if they were consistent about it, but with hydrogen, they can't. Covalent compounds with hydrogen, they actually tend to treat them as if they're ionic compounds. It's kind of weird. So,
Warped chemist humor.
yes, indeed.
Yeah, and it's kind of.
Oh, yes, go ahead.
Oh, sorry. It's just kind of like languages. Languages, they've evolved where, in general, you can find some logic to it, but there's, sometimes there's not a lot of logic to it. So it's the same in naming in chemistry language. There's a little bit logic to it, but it's not always. And so yeah, it's so if we're trying to find logic, probably we won't find it.
Yeah, there are idiosyncrasies that creep in. The English language is notorious for that. So that's a good point. All right, what about PI3? What do we got there?
Phosphorus triiodide.
You got it. Phosphorus triiodide. 2 I's. Excellent. Well done.
Good job, guys.
Well, that's all. That's all that we have for this, and you all did a great job. Now, one of the things that I would recommend is that when it comes to this, you guys have, when it comes to naming, you really just need a lot of practice. That's what it comes down to. Practice makes perfect. The more you practice, the better you're going to get with it. And you want to get to the point where it's basically like automatic, like it doesn't take any thought or time for you, especially later on. Because admittedly, this type of naming is going to be sticking with you for the rest of chemistry, basically. If you're going on for any further chemistry courses, or even for the rest of the semester, you're going to have to know how to name ionic and covalent compounds. So this is going to be very important going forward. So where can you find some awesome practice? Well, look no further. I have the deal for you. I'm going to share my screen real quick. And it turns out, if you go to our website, which you can access by just typing into your search engine, you can type into your search engine TCC space SE space science. And I like to use DuckDuckGo, but you can use Google or anything else. But the TCC SE Science Learning Center Google sites, you click on that, and it comes to TCC SE Science. And from here, if you click on Chemistry Web Resources, scroll down to 1411 under Practice Problems, you will get a wide array of naming and writing formulas practice. There's Ionic Formula Practice, Ionic Formula Practice 2, Name Ionic Compounds, Ionic Compounds Review, Covalent Compounds Formulas and Naming, Mixed Ionic and Covalent Naming, Mixed Ionic and Covalent Naming Formulas 1. So as you can see, there's a lot, and each one of these has like, maybe 56 examples that you can go through. And this is really nice because it really gives you an opportunity to practice. So I know this is a lot, but I would recommend you spend some time practicing. And all the answer key is here for you to check yourself So you can see if you really understand it. But I would definitely spend some time pounding that in to your head, because it does take a significant amount of practice to really lock something into your brain. I think they say that to commit something fully to long-term memory, it requires you to repeat it at least at a very minimum. The research, I think, indicated it was at a very minimum about 75 times or more to commit something to long-term memory. Um, and even to commit something to short-term memory, it's at least 25 times. So if you think about, there's actually several different types of processes here, naming with transition metals, naming without transition metals, naming ionic compounds, naming covalent compounds. Even if you're just to commit it to short-term memory, you need to do like 25 examples of each of those. So I would definitely really encourage you to look over those. And if you honestly, if you want a little bit more help, or if you want a little bit more review on that, there's a really great video tutorial library here. And one of the videos that we have, some of the videos that we have that are really great for that are my good friend Tyler DeWitt. He actually has some excellent ionic and covalent naming stuff. Actually, it's not here, sorry. He does have some ionic versus covalent molecules, but the naming and writing of formulas is actually in molecules, compounds, and chemical equations. Okay, here we go. There we go. And here we go. Write ionic formulas, writing ionic formulas with polyatomic ions, transition metals, writing ionic formulas with transition metals, naming ionic compounds with transition metals, and some more practice. So there's a lot of really good videos here that break things down if you feel like you need a review. Plus, of course, you can always go to the workshops and events tab and check out our previous workshops, including this one here. We have our sig figs workshop from last week, and we have our ionic and covalent one this week. I'll be posting the video probably sometime tomorrow. I'm just going to make a few minor edits to cut out like some of the unnecessary dead space, and also like when I say things that make myself sound stupid, which is a lot. So there might be a lot of editing. But anyway, yeah, I'll be posting that probably sometime tomorrow.